here we go, counting models, user abstractions, and blockchains. So how do we represent users? Okay, so what we talked about so far, this is a lot of, Josh had covered a lot of this. We had the blockchain structure, we have this game theory aspect, which we won't really deal with today, and cryptography, which is important for today's lecture. So yeah, we're going to put a lot of these things together continuously throughout this module, and so this is one place where we're going to, again, try to put all the stuff that we've learned so far together. Okay, so where do we go from here? I think I just said that. Let's put them together into something cool. All right, so now that we have this like kind of decentralized tamper-proof state machine, which we kind of talked about earlier, which we can kind of vet out, we want to think about ways which we can formulate a state and a state transition in terms of representing users. So we've been going through the blockchain from scratch stuff. We're dealing with initial state and state transition, and that's going to be really important for this lecture because the two models we're going to talk about have a different way to transition the state in a more general sense. So there's two different paradigms, but we'll talk about this first paradigm. So we craft a model in which the system acts as a global trustless verifier. After we get done with this talk, you can maybe argue with me if I'm correct on that, but this is kind of the way I like to think about it. So let's look at what this global verifier thing looks like. Okay, so hopefully you can see some of this. But so we have person A and person B. We have this system, and we have like kind of a couple actions down here that person A wants to do. I'm going to use money in this example, but just keep in mind that I'm just using it for the sake of example in some cases. We don't have to think about this entirely as money. This is one of the important things. So person A has an action which they want to send 10 over to person B. And so you'd probably think about like, why would you put money in like 3 different bins like that? Wouldn't we just say that there's, can I do math? Yeah, 22, 20, yeah, 23, whatever. Why do we do this? Well, that's kind of the point of this talk, but you'll kind of see later. But I just want to kind of show this first, and I'll show it again afterwards. But we have these different monies that person A has. We'll just say that they're bills with like their name written on it, and we want to send 10 over to person B. So our action is that since we have like these individual bills, we couldn't spend 3 or 5. We actually have to spend the 15, right? When we do that, we can kind of pass this over to this verification system and say, like, are we allowed to actually, am I allowed to do this? The system can kind of look and see that, oh, maybe I have this 15 with my name on it. A person A PQ just means like person A's public key. We're going to get more into, we went through actually public-private key cryptography. So that's how we establish this person's name. And then person B will receive 10 monies. But we'll talk more about this. Okay, cool. All right, how will we do this? This is kind of a weird slide, but I'm going to try to do this as best as possible. So there's kind of these two parts to this system. I actually would like to start with point 2. So you have data, which can be altered, along with a key stating who can alter it. Okay, that seems pretty simple, right? So you have some general piece of data, and you have this key attached to it to say, like, who can actually do stuff with this? That is something that we call an output. And then we have this thing, an input, which I'll try to describe concisely. So you have some uniquely identifiable piece of data. Okay, so we just have some generic, unique data with a signature attached. So saying, hey, I signed this, I can spend this thing, is kind of where I'm getting at with this. So yeah, in other words, we have some data that can be altered only by a specific entity. So we want to provide proof that we can alter it, right? So if we look at bullet point 2 again, we had this piece of data and only a certain person can actually alter it. So we have this other thing called an input, which is you have to actually provide proof. hey, I'm this person. I can modify this data. So that kind of, it'll get better. Just trying. So I will say that these two systems that we're going to talk about, one is, I think, just very intuitive for us as it being involved in computer science. And this one is a little bit weird. Maybe Josh can, yeah. I think this one is weird, but once you wrap your head around it, it starts to make a lot more sense. Okay, is this our state? What is our state? So our state is from this previous slide back here. You have data which can be altered along with a key stating who can alter it. So our state in this system is actually a bunch of those things. So some value or data which can be altered via a particular specified owner. Same thing again. So that's what our state looks like. So like this is a table that I kind of call this like the state table. So you have your keys, you have your values. I like to think of for me, I kind of think of the underlying blockchain structure as, you know, we call it a state machine, we say state, it's a database, it's a key value store. At the end of the day, when we get into the layers of storage in Substrate, you'll be like, okay, this is a database. If you're a computer science person, yeah, you're just like, oh, this is a database, great. So this is kind of what the system looks like. This is what the state looks like. So you have some keys, which are hashes of these things that we call transactions, which we all know what a transaction is. We'll look at what the structure of a transaction actually is coming up. But for now, you can kind of see you just have your key, you have a hash of this thing, and then the value is, again, pub key with a value attached. So in this case, we have, you know, pub key 5, it has a value of 100. We have pub key 1, which has a value of 33, but then we also have pub key 1, which has a value of 74. So like, again, pub key replacing with like your name, it's like, oh, look, I have different entries into the state, which all belong to me. Yeah. So you'll kind of notice this highlighted one. You're like, why is there a collision there in the hash table? This wouldn't happen. This actually wouldn't be the look of the table, but I'm showing that if you don't do something very specific, you can come into a point with this system where you'd have a collision. So there's a way that we actually get around that. So anyways. So what is the notion of a user, a public key, and all of the uniquely identifiable data which can be manipulated by that key? So if we kind of go back here, we could say that a user is pub key 1, but again, all of user pub key 1's data is actually spread around the state. So you'd actually have to like kind of aggregate that to get a view of, say, if this was money, balance, right? Okay, so we described somewhat of the state. Now let's talk about how to transition the state using this new kind of verification model. So again, I was just trying to lay out like what the state looks like, and now we talk about how we actually like make the state transition happen. Okay, so transaction, I think Joshy talked about this, but I used to get kind of confused by it. There's a lot of like synonyms for transaction. Extrinsic, kind of, yeah. So again, it's just a request to change the state of a system is the way that I look at it. So what does a transaction look like is basically how we map these inputs to outputs. And a transaction in this model is a list of inputs and a list of outputs together. Okay, so what were those input-output things again? So so here's what a transaction actually looks like. So you have, in the first part, you have output 1. This would be like, so this would be like Andrew with a value of 10. And you have a signature attached to say like, hey, I want to spend this thing. You basically have a list of these things. And then as an output, you say who is going to basically receive these things. So let me just get to the next slide because I think, yeah. So what happens in a state transition for this kind of model? So you have the inputs which signal which outputs from the state will be consumed. So your inputs basically say like, all right, which bills are we going to spend in this money system? And once you spend them, they get deleted. They don't kind of like stick around. So we also must verify the signature given in the input with the corresponding specified output's public key or owner. So we, if I say I want to spend this bill, I have to show proof that I am that person. Again, I'm kind of specifying that. So in the input, we put that signature. We must verify that the resulting state, which has been provided, is a valid one. Okay, this is an important one. And this is defined by you. So in the money example, a simple one would be, I guess kind of in the second bullet point here, you can't just like take a $10 bill and then say, hey, I'm creating $20 out of it. That's not possible in the money system. I mean, maybe it's possible in some money system, but yeah, not generally. So, but I hope you can kind of see that it doesn't just have to be money, right? Like say this was something else that needed to be consumed, and you define the logic of what is a valid output. And I guess what I'm trying to say is that we have two different models here, and in this model, you don't just submit input to the system, but you also need to tell the system what the output is, and the system will verify that this is actually a valid output. That can be kind of different than how we think of traditional kind of systems, where it's like, I submit some input, like a computer, and tell me what the output is. Like, do all the stuff for me and output it. And in this case, you actually have to tell, hey, this is the input and this is the output, so you need to compute that you have a valid output. Okay, so we kind of come back to this diagram here. So I guess the most important part is the bottom, which I hope that people could see. But you have state 1, which is representative of this money example up here. But below you have state 1, right? And in the initial state, you have 3 outputs. You have $15, you have $3, you have $5, and they all belong to person A, kind of similar to up here. And so if we want to actually modify the state or make a transition, say send 10 to person B, then what we need to do is we submit as an input that we want to spend output 1. Okay, so we say I want to spend 15. That's kind of the example that we used, right? But I also need to submit in the transaction the output. So what's going to be the situation? Well, I only want to send this person 10, right? But I have a dollar, I have $15. So I need to give myself back 5, or maybe I want to burn it. But in most cases, maybe you want to receive your change back, unless you're being very generous. And so then we have our state 2, which is that we never spent output 2 and 3 over there. If you look, 3 and 5, we never spent that. We only spent 15. So those remain in the state. And then our new state has that person B now has 10, and person A has a bill worth 5.
What type of information is contained in the signature?
Oh, like what's the message?
Yeah.
Yeah, so you're signing the actual full transaction. So you create the inputs and outputs, and then you sign that.
I don't know, I'm a little confused. When you sign the whole transaction, the signatures are in the transaction. So what are you signing?
If I understood right, you're saying like, you're looking at the pink box, right? That's the transaction. And you want to know, and there's that part labeled SIG, so that's a signature, right? So you're saying like, what is the signature over? And Andrew's answer is basically right. It's like the entire pink box, but then you're like, wait a second, there's this problem. Like, how can the signature be over the whole pink box when the signature itself is in the pink box? So here's how we get around that. We basically construct that entire pink box, and we fill in the spot that says SIG with all zeros, or whatever. Choose any magic thing you want there, but like typically it's all zeros. And then you sign the whole pink box, and then you mutate it, like you put the signature in where the zeros were. And so I think the second part was like, what if there's multiple inputs? You just do that same thing multiple times. You like fill all the signatures with zeros, sign it with every key, and then put those signatures in the right spot.
Okay, good.
Two questions. One, to find a person's an account's balance, you can search by their public key or address, and then you simply sum up all the outputs, correct?
Yeah.
Okay. And question 2, so a given output will persist forever in state until it is included in some transaction where it is consumed and no longer, and then that's the end of it, and a new output.
Yeah, you can kind of, it like gets destroyed and like little babies come out of it. I don't know, that's how I, how I think about it.
Thanks.
Okay, so that whole thing that we're talking about is this thing called UTXOs, which which you might have heard. It's a system that's used in Bitcoin, it's used in a few other blockchains. So yes, so whenever someone mentions it, hopefully you can kind of have a little bit of a mental model of what UTXOs mean. Okay, which again means unspent transaction outputs. Okay, so second paradigm. We craft a model which the system acts as a computer. I like to think of it this way. And by submitting some input, it will determine the result from the input. Okay, cool. Instead of, in the previous model, like we said, we had to give it the input state and the output. We actually had to kind of be the computer a little bit, the client. Yeah. Okay, so let's make it a little bit more intuitive. This should be, I think, a lot more easy to understand. So instead of doing the computation ourselves, then submitting to the system to verify, by understanding the present state and then computing the resultant state and then submitting it, why don't we just let the system hold our state information or data in the form of an account, and we submit requests and data to the system. Yeah, so this is like we can let the system be a computer, nice and easy. Okay, so what is the state then in this system? Well, it's a lot simpler. You have this account, and then you have values associated with it. So yeah, we'll look at it a little bit. So this is kind of what it would look like a lot more in this accounts model. You have a bunch of keys, they're hashes, and you have a bunch of values associated with it. Of course, it doesn't need to be like a uint or something, but you kind of get the picture that we have some key value stored now that just looks similar to what we have seen all the time. Okay, so now that the state is much simpler, and in my opinion, what about transitioning this state as compared to the last one? Okay, what does a transaction look like now? All right, cool. So we have kind of a similar model, but in this, we're using this new accounts model, we call it. So instead, again, I want to send, person A wants to send money to person B, or the green guy wants to send money to the blue guy. And so the action is to send 10. So instead, we send our request to the system, and I'll tell you what that request would look like. And the system would then do some compute instead of just kind of verification. And it would basically check, okay, hey, does this green person have 10? Okay, yes. Take 10 from them, and then add it to person B's balance in that kind of hash table. So you have your initial state here, state 1. Person A's public key has 15. They're not all separate anymore. You then, in the transaction, you send a signature for person A along with the amount that you want to send, and then where you want to send it to, right, person B. And then in the second state, now you have person A has 5, and person B's public key is assigned 10. Sure, yeah.
You said it's about, in the transaction is the amount you want to send, but I see that you send 15 in the amount in the transaction and B takes 10.
Oh, my bad,
So
that's a typo. That's a typo,
right?
Yeah, it should be amount 10, sorry about that. So what happens in state transition? We kind of talked through it, but we still verify, but maybe we verify less, determine more. So we check the signature of the message, or computational instruction given, yeah. And then we verify that account that is being requested to be modified is the signer's account. Okay, is this person the person who can actually modify this key value? Then we perform the computation necessary by the instruction and updated the account accordingly. So we're kind of like, yeah, again, we have the state, we send a computer instruction and say, modify this computer thing, do your computer stuff. Okay.
For chains that use the account model, is there a process by which they kind of check the sanity of the values that are assigned to certain accounts against the history of the transactions? Or is the assumption that they will never go out of sync?
We haven't got this yet to consensus, but if everybody's kind of Byzantine, which I think the situation you're presenting is, then our system breaks down, basically. So there's some guarantees that the rules by which we agree on the present values that are in the database, and if those kind of like baseline rules are broken, then the system is compromised. And we've seen that in blockchain.
Yeah, that makes sense. Thanks.
Yeah.
I also just wanted to point out that this question is like not specific to the accounts model. Like it could also be about UTXO or any state machine at all. Like it's more a question about like what if all the nodes like collude to execute an invalid transition.
Yeah, yeah.
In the account model, does the destination account must exist before sending some money?
Depends on the system. I think historically there hasn't been like any checks there, so you could just send like the smallest units of balance to any account and it would just be existent. Newer models have the concept like existential deposit. So if you send less than a certain amount, it's effectless. It's almost as if burning that amount. So it depends on the implementation.
Yeah. So now let's kind of compare the two models. This is kind of my favorite point, because there's a lot of heated debate on which one should be used. And so let's just take an objective view at what we think are the pros and cons of each. So size, storage. I don't really got to say much, but UTXOs are much heavier in terms of raw data stored plus transaction size. Can anyone think of why that may be the case?
So in UTXOs, we may have, I don't know, like 10 and spend in outputs, and they all equal, like, I don't know, 100.
Right.
And in accounts, we just have that 100, right?
Correct. Yep, absolutely. So in the accounts model, yeah, you just have a single balance or data value associated with a key instead of like all these separate values with metadata associated with it. So you get, in the UTXO model, yeah, you have this specified unique ID with it. And in the UTXO model, as more items are consumed, more are being, well, this isn't actually true. More are being produced. That might be the case. That could be frequently the case, but maybe not. But your storage size can kind of grow much more quickly because for a single balance, we might have tons of entries in the database. Transactions are generally more simple in the accounts model because no output state must be specified. But this, again, I guess we'll see when we get more into Substrate, you can get some very complicated transactions as well, but yeah. Okay, privacy. This is a good one. So both have their merits in different ways regarding privacy. Can anyone think of an advantage of one with regards to the other for privacy? Maybe some pros, cons?
But you're constantly destroying the wallet, right? So like, that's maybe a little more secure because something's changing all the time. That's
a good, yeah. I mean, I think you're onto something there.
So
So the accounts model in its default state utilizes like the efficiency of address reuse, but it makes transaction history kind of easy to aggregate. So yeah, it's very easy to just update someone's balance and change it, but you're doing a lot of actions on the same account, basically. UTXO model can utilize this change address, which we kind of talked about earlier. And I'm also saying here that, again, if you're not using that technique, it's very easy to see, like, and very transparent to see how this thing got to where it was. So if you're just using the same address every time to send yourself stuff, then that would be apparent. Accounts model has a way of doing privacy where, again, in accounts model, because everything is like one value is the same as another value, it doesn't have any kind of metadata attached to it. You can do this thing where you can kind of pool everybody's money into a single account, and then it all looks the same, and then everybody can kind of take out from that pool with new addresses, and you can obfuscate that way, which is Tornado Cash, and that, you know, we got sanctioned here, so. But yeah, so there's ways to do it in both models. Okay, so smart contracts, or I think this is supposed to be general compute platforms. So based on all the previous information, can you think of a model which is more intuitive and seems to make more sense for just a general compute platform? So yeah, so verification is easier if all that is needed is to check a value associated with the public key, rather than verifying it if an output has been consumed. Do I have it here? Yeah. So if you have to, if you're utilizing the system to do compute, then it can be very easy if you just assign, say, a piece of code or a blob to an address. And this is, I don't want to go, I guess, too much into like smart contracts, but it is easier to do this kind of like general compute stuff on the accounts model due to the nature of kind of the mapping. You don't need to go and destroy something. And honestly, I'm not going to, I don't know enough about smart contracts and UTXO blockchains, but I do know it's very hard for many reasons. So, parallelization. Does it seem like there's a model which would be easier to parallelize?
Well, if you agree on which transactions one process will use and which transactions another process will use, they can just parallelize and do different, with the same money from the same person, send it to different places. But if you need to agree on the specific history of an account, then you cannot really parallelize it. You need to have a specific straight line for that account.
Right. Yeah, so, let's go to the answer. Yeah, so multiple transactions which touch a single account, generally, I won't say all the time, should be executed in sequence. You can kind of think of this like, say I'm trying to send like, I don't know, 10, 10, 10, 10, 10 to everybody, or maybe to this person, then this person, then this person. There's kind of a sequence there of actions which are touching an account. So there's a dependency graph. But if you have every, UTXO has its own kind of life, I guess you'd say, inside the database. So if a transaction is just touching, say, my $10 bill and it's just touching Joshy's $15 bill, and then it doesn't, it's very easy to kind of separate those out because there's no dependency. So, conclusion, both are good depending on the use case. At the end of the day, just a state machine, just different kinds. So,